Now in this video lecture we will talk about theory of catalysis, right? In this video lecture we will talk about theory of homogeneous catalysis, right? So theory of homogeneous catalysis, under this comes intermediate compound formation theory, right? But first let's just first talk about how catalyst helps in increasing the rate of reaction, right? We know that the important requirement, right, the energy requirement for a reaction to take place is that the reactant molecules should possess a minimum amount of energy called as threshold energy, right? And the reactant molecules that do not have energy equal to threshold energy, then we need to supply that extra amount of energy so that their energy becomes equal to the threshold energy, right? That extra amount of energy is called as your activation energy, right? Now what happens in the presence of catalyst? In the presence of catalyst, we have to provide the activation energy to the reactant molecules less as compared to the reaction taking place in the absence of catalyst, right? So in the presence of catalyst, the catalyst provides an alternate path, right, for the reactant molecules to react, right? That alternate path have less activation energy, right, and less threshold energy, right? We have done this diagram before also, right? It looks somewhat like this, right? Whereas say this is your, we are measuring from here, this is your energy of reactants, right? But these reactants need to cross this energy barrier, right? And till here the energy is your ETH. ETH is your threshold energy. This is your ER, and ER if less than ETH, right? If the energy of the reactant molecules is less than ETH, right? Because some molecules would be having energy equal to ETH and they will form products, right? Now for those molecules that do not have energy equal to ETH, this case, then we have to supply an extra amount of energy, right, to the reactant molecules, which is known as your EA, activation energy, right? Now this is the energy of the reactant molecules, right, but they have to reach till this point, right? So the extra amount of energy that we need to provide is this, right? If you look at this, this is the energy that the reactants already have, and till this point they have to reach. So this is the extra amount of energy that they need, right, so as to form products after gaining energy equal to threshold energy, right? So this energy, right, is known as your activation energy, right? Now in the presence of catalyst, right, what catalyst does is it will lower down this EA, activation energy, or it will lower down this ETH, right? It's one and the same thing. It will, how it will lower down this activation energy or threshold energy? By giving an alternate path to the reactant molecules to react, right? And this alternate path would be somewhat like this, right? This will represent an alternate path, and this path would occur in the presence of your positive catalyst, right? In the presence of positive catalyst. So now if the reactant molecules already have this much energy, now they need this much energy, right? This much energy, which is your ETH, in the presence of catalyst. So the extra amount of energy is this much. This much they already have, right? This much energy they already have. They need to reach at this level. So the extra amount of energy would be this much, right? Which is much less if you compare the previous one, right? This was the previous one. This one was the previous one, right? It's here, right? And it's here, this. And in the presence of catalyst, it reduced to this much, right? So presence of catalyst reduces the activation energy or the threshold energy, right? Now in the presence of this alternate path, right, which is introduced by the catalyst, more reactant molecules will have energy equal to threshold energy, right? So they can form products, right? So the reactant molecules that have less energy, they will follow this path, right, to form products, right? Now this is the positive catalyst, right? Now we know that there are something called as negative catalyst. We have done in the previous lecture. Negative catalyst is something that decreases the activity of a catalyst, right? It will, due to the presence of negative catalyst, right, the rate of reaction will slow down, right? So what a negative catalyst will do, if you look into the graph of negative catalysis, it would be, if this is without the catalyst, right, then suppose this is the graph, right, this is the energy of reactants, right, and here it is ETH, threshold energy, right? So this is your activation energy, right? Now in the presence of catalyst will increase the threshold energy, right? Presence of negative catalyst, this is your negative catalyst. Presence of negative catalyst will increase this level of activation energy or the threshold energy, right? Now the threshold energy, the level of threshold energy is here. Earlier it was here, now it is here, right? And if you look at the activation energy, earlier it was this represented by red line, now it would be this represented by green line, which is much higher compared to the previous one without the negative catalyst. So negative catalyst is doing reverse of positive catalyst. It's increasing the activation energy and the threshold energy. So more activation energy is required in the presence of the negative catalyst. So less molecules have energy equal to activation energy or equal to this threshold energy, because the level of threshold energy has gone up. Less molecules will have now energy equal to threshold energy. So less molecules would be able to form products, right? So by increasing the threshold level of energy or the activation energy, negative catalyst will decrease the rate of reaction, right? Now this is about the basics of energy requirements for a chemical reaction to take place, right? Now we have understood positive and negative catalyst both. Now let's see about homogeneous catalysis. Homogeneous catalysis is explained by a theory. We call this theory as intermediate compound formation theory, right? Intermediate compound formation theory. Intermediate compound formation theory, so an intermediate is formed, right, in the presence of catalyst, right? We get to know from the name itself. Now what happens is, suppose two reactants are reacting in the presence of catalyst. So what catalyst will do to increase the rate of reaction? Catalyst will first react with either of the reactants, right, with one reactant to form an intermediate compound, right? Then that intermediate compound would be unstable, right? Then we know that if a compound is unstable, then either it will decompose, or if it has something to react, it will react with the other substance. So here either that intermediate compound will decompose to form product regenerating the catalyst, or it will react with another reactant to form product and again regenerating the catalyst, right? So this is your intermediate compound formation theory, right? And the intermediate compound, right, being unstable, will decompose readily. We have already done this. Suppose your A and B are reacting in the presence of X catalyst to form product AB. Now this X catalyst will react with either of the reactants. Say it reacts with A to form AX, right? Now this AX is your intermediate compound, right? So this intermediate compound will either decompose to give product, right, or it will react further with another reactant, right, to form your product, right? So here basically the catalyst combines with one or more of the reactants, right? It may react with one reactant with either A or B, or it may react with both the reactants A and B, right? So here this intermediate compound that gets formed, it will further react with, since it's an unstable, so either it will break, since it's an unstable, so either it will break, and we know that unstable compounds are very reactive, or it will react with another reactant, right? It will react with B, forming AB, which is your product, plus regenerating the catalyst, right? This is your catalyst. So catalyst is recovered as it is, forming the product AB, right? So what it basically does is, the involvement of this catalyst in the reaction lowers the free energy of activation, right, and hence accelerating the speed of reaction, right? This is what it's doing, right? Here the intermediate compound that gets formed has lower energy of activation, right? So it will immediately decompose, right, to form, or I'm sorry, it will immediately react with another reactant, or it may also decompose to give you product and regenerating the catalyst. Let's take an example of homogeneous catalyst. It's oxidation of sulfur dioxide to sulfur trioxide, right, in the presence of nitric oxide. This is your lead chamber process, or this is done in contact process, right? So here this is your catalyst NO, right? So NO, as per this theory, will react with either of the reactant to form an intermediate, right? And that intermediate will react with, either will decompose or will react with another reactant to give you product regenerating the catalyst. So how this reaction will take place is, NO will react with oxygen giving you NO2. Now NO2 is unstable and it will react with sulfur dioxide giving you sulfur trioxide, right, plus NO, right? NO is your catalyst regenerated and product is your sulfur trioxide, right? So oxidation of sulfur trioxide is done in the presence of catalyst nitric oxide, right? Similarly, if we take another example, let's take example of formation of diethyl ether from ethanol in the presence of concentrated sulfuric acid, right? So ethanol, we know the formula C2H5OH, it will react in the presence of sulfuric acid, right, to form C2H5O C2H5, diethyl ether, right? Let's see how this occurs. Two molecules of ethanol. This ethanol, sulfuric acid is your catalyst. C2H5OH plus H, we can write it like this, HHSO4, right? So it reacts with it, giving you C2H5, right? It forms C2H5HSO4, right? This is your intermediate, right, having high energy. It's a unstable compound, so it will react with another molecule of the reactant, which is your again C2H5, right, plus C2H5HSO4, right? So this hydrogen will react with this, because finally the catalyst should be regenerated and a product should be formed. C2H5O, C2H5 plus H2SO4. Catalyst is regenerated, right? So this is an example of homogeneous catalysis, where your reactant is liquid and your sulfuric acid is also catalyst which is liquid. This is your example of homogeneous catalysis, right? So I hope homogeneous catalysis is clear, right? And in the next video lecture we will do the theory of heterogeneous catalysis. Thanks.